Hello, in this video we're going to continue on with our differential equation topic, but specifically in here we're going to talk about separable differential equation. So separable differential equation is an interesting equation, and we're going to learn about lots of different types of differential equations. In Calculus 2, we really don't do a lot of different types, but we're going to talk about separable differential equations here. The reason why these ones are really great is because you use calculus to solve them. So you use calculus to solve a couple other ones as well, but this one you use predominantly a lot of calculus. So you're going to use a lot of integration. So let's go ahead and do a quick definition. I'm going to zoom out here to make this a little bit smaller because my large handwriting looks a little juvenile. So let's go ahead and express. I like that better. That differential equation. So let's say that we have a first order differential equation, dy dx. We'll say this is a function of x and a function of y. So a function of x and function of y, very similar to how we said f of x, y, f of x comma y before, but now instead of saying f of x comma y, we're saying it's a function of x and a function of y. So I think it just deleted something again. Express, okay, I hope it didn't delete anything. I gotta really tone my program back. So let's go ahead. We can say that this first order differential equation is separable. And before I write out the more formal definition, I'm just going to tell you what I think. Is that if you can get the x's and the dx's on one side of the equation, and you get the y's and the dy's on the other, then this is separable. And I know this sounds slightly petulant, but it really is. It really is. It just makes so much sense to me. If you can get your x's and your dx's on one side and your y's and your dy's on the other side, then you have a separable differential equation. So let's just remember that. So as we continue on, we can say that we have a separable differential equation. So let's assume that dy over dx can be split up, and dy over dx is a derivative of y up on top and a derivative of x on the bottom. And it just disappeared. Better prevent that from happening. Maybe it's just zoomed in too much. So let's just hope that's all it was. So what we're able to do is that I always think like this is sort of like cross multiplying. I'm going to cross multiply my dx on one side. So I have dy is equal to g of x times h of y times dx. So hopefully you're seeing that my goal is to get the x's and the dx's on one side. If I can get the x's and the dx's on one side, then I feel really, really good about my possibility of my differential equation being separable. So now if I want to get the h of y on the other side, I'm going to go ahead and divide both sides by h of y. So notice here, this will give me dy over a function of y is equal to g of x times d of x. And the neat part about having these derivatives, derivative portions in here is that if I want to get rid of them, all I have to do is integrate on both sides. So if I want to get rid of them, I can integrate on both sides. And that makes this very beautiful, because this allows me to solve my differential equation. So if I'm able to separate my x's and my dx's on one side, my x's and my dx's on one side, and my y's and my dy's on another side, we have a separable differential equation. There is a more formal explanation to this. However, I just like to keep it easy, keep it simple and clean. So let's go ahead now and identify and solve our first differential equation. So let's go ahead and start with an example. let's go ahead and start with an example. Let's say we have dy over dx, so this is going to be a first order differential equation, and this will be equal to a function of y times a function of x. So notice here, this is a function of y, and this guy over here is a function of x. So that's a horrible, there we go, I want to make sure this looks clean. A function of y, and the second guy is a function of x. So if we could readily separate the x's on one side with the dx's and the y's on the other side with the dy's, then this is going to be a separable differential equation. So let's go ahead and try this tactic out. So the first thing that I want to do here is that I'm going to cross multiply my dx on both sides. So I'm going to have dy equals 2. It's going to be equal to 1 plus y times e to the x now times dx. I want to isolate my x's and dx's on one side, so I'm going to divide both sides by 1 plus y. So this now will yield dy, so this will now yield dy over, there should be equal signs here, dy, actually should be an arrow, dy over 1 plus y is equal to e to the x dx. dy over 1 plus y will give us e to the x dx. Notice we got our y's and dy's on one side and x's and dx on the other side. If you want to solve, the rule just states integrate both sides. Whatever you do to one side, you must do to the other side. So hopefully we see on this side that this is an easy use substitution. So if u equals to 1 plus y, du equals to dy. So we have our du up on top, we have our u on the bottom. So this will be equal to the ln of the absolute value of 1 plus y, and my program keeps deleting. My program keeps deleting. And this will be equal to the integral of e to the x dx is just e to the x. But remember, whenever we have an indefinite integral, we're always going to add a constant of integration on both sides. So this gives you ln of the magnitude of 1 plus y. This will equal to e to the x plus a constant. So some of you may say, what happens if y is less than or equal to -1? So usually there's going to be a declaration at the beginning of this problem, and they're going to say that y must be greater than -1. Otherwise, you can't really solve this. So just be cognizant that normally they're going to have a restriction on here, because people might say, what happens if y is equal to -1? So in the problem, they might usually say that y must be greater than -1. So this is going to be the solution to our equation, our differential equation. And notice this is a general solution. This is going to be a general solution. How do we know it's a general solution and not a, wow, this is bad. So how do we know this is a general solution, not a unique solution? And the fact that we know it's a general is because we have this constant of integration. So I'm going to cut this video a little bit short because I'm having technical difficulties. And hopefully we recognize a relatively easy way to identify a separable differential equation.